Chapter 12.3, Measures of Dispersion. Measures of dispersion are used to describe the spread of data items in a data set. Think about this. Think about the two cities, Houston, Texas, and Honolulu, Hawaii. Okay, both cities have a mean temperature of 75 degrees. However, the mean temperature does not tell the whole story. The temperature in Houston differs seasonally from a low of about 40 degrees in January to a high of close to 100 degrees in July and August. By contrast, Honolulu's temperature varies less throughout the year, usually ranging between 60 and 90. So the measure of central tendency is usually not enough to talk about the differences between two sets of data. Now, two of the most common measures of dispersion are the range and the standard deviation that we're going to discuss. So, a quick but rough measure of the dispersion is the range, the difference between the highest and the lowest values in the data set. For example, let's say Houston's hottest temperature was 103 and its coldest temperature was 33. To find the range, I just need to subtract that lowest value from that highest value and to find that they have a 70-degree range. If, let's say, Honolulu's hottest day was 89 degrees and its coldest day was 61 degrees, then to find the range, if I subtract those two values, we get 28 degrees. So even though Houston and Honolulu's mean temperature is 75 degrees, with the additional piece of information that the range of temperature in Houston varies by 70 degrees, but in Honolulu only 28 degrees, that gives us a little more information into our data sets. Okay, a second measure of dispersion, and one that is dependent on all of the data items, is called the standard deviation. The standard deviation is found by determining how much each data item differs from the mean. So let's look at a couple of sets. Let's say we have, let's see, these data items, right, versus another set with these data items. Notice the mean for each one. Add them all up and divide by 4. So here's 10, 20 divided by 4. So the mean is 5 for this set. Same thing here. I've got 10, 20. So 20 divided by 4, the mean is 5. And if I wanted to find the range of this set of data is 9 minus 1 or 8. And the range for this set of data, 9 minus 1 or 8. So notice I've got the same mean, the same range, but my data set is pretty different. So a better measure of dispersion would be what we call the standard deviation, because it's dependent on all of the data items. All right, so here's the steps to find the standard deviation. Here's a little formula that will be explained after we look at the steps, and it's easier usually, instead of plugging into the formula, I'm going to have to make a table to actually get the information to plug in to the formula. So the first thing I want to do is find the mean of the data items, which we've done here. Find the deviation of each data item from the mean. So I'm going to come over here and I'm going to make myself a little chart. Right, here's my data items. So I'm going to list my data items. And then the deviation of each data item from the mean means how far is the mean from each one of these. And again, we subtract to find the distance. So 1 minus 5 is negative 4. 1 minus 5 is negative 4. 9 minus 5 is 4, and 9 minus 5 is 4. Now, if I want to find the average, the mean of this distance, notice if I added these up right now, I would get 0, right? 2 negative 4s, 2 positive 4s would be 0. I would get that every single time because that's exactly what it means to be the mean, right? It's in the center of your data. So the average of those distances of each point from the mean would be 0 because that mean is the center. So to account for that, let's square each one of these values to get rid of my negatives. And then that's why in the end we're going to square root. We're going to square them to get rid of the negatives, and then we'll square root to get back to where we need. So 16, 32, 32, 64. Then I'm going to add them all up. Okay, so we squared each deviation. We summed the squared deviation. Now we're going to divide the sum by n minus 1, where of course n is the number of items in your set. And minus 1, statisticians have just found that actually gives a closer approximation. So that's just something I'm going to remember that's standard in my formula. And divide by instead of n when if I was finding the typical average. But remember, I've kind of mixed it up a little bit by squaring everything. So divide by n minus 1. So I'm going to take 64 divided by 3. And the square root of that is, let's see what the square root of that is. 4.62 about, rounded to the hundredths place. 4.62. Okay, let's do the same thing for our other set of data. First of all, I need a table where all of my data items can be listed individually. Okay, then I'm going to find their deviation from the mean, how far each one is from the mean, since my mean is 5. 1 minus 5 is negative 4. 4 minus 5 is negative 1. 6 minus 5 is positive 1. 9 minus 5 is 4. Notice again, if I added them up, I'd get 0. So I need this extra step over here in my table to get rid of those negatives. I can square 16, 1, 1, 16. When I add these up, I get 32, 33, 34. So I want to find the square root of 34 divided by 3 because I still have 4 data items. So 4 minus 1 is 3. And that is 3.37. Okay, so even though this set of data had the same mean and the same range, different standard deviations. And of course, the higher the standard deviation, the farther the spread in the numbers from the mean, which I can see that with these data sets. Excuse me. Okay, the standard deviation of a sample is symbolized by S, while the standard deviation of an entire population is symbolized by this symbol, which is the Greek letter sigma. And we're always going to be concerned with, in this chapter, our data will represent samples, so we'll always use S for the standard deviation. Okay, let's see if we can apply this. Now remember, as the spread of the data items increases, the standard deviation gets larger, right? If they've got more spread between them, it will have a larger standard deviation. So this asks us to find the mean, the range, and the standard deviation for the data items in each of the 3 samples. Then describe one way in which the samples are alike and one way in which the samples are different. Okay, so the mean, I need to add all of these up. 6 plus 8 plus 10 plus 12 plus 14 plus 16 plus 18, and divide by 1, 2, 3, 4, 5, 6, 7. Okay, let's do that. And we get 12 for the mean. The range, this is my largest and that is my smallest, so the range is just subtract the largest and the smallest, and I get 12 for the range. And now I have to find the standard deviation. To find the standard deviation, it's going to require making a little chart, right? A table where I can see each individual data point, 6, 8, 10, 12, 14, 16, 18. Their deviation from the mean. If the mean is 12, 6 minus 12 is negative 6. 8 minus 12 is negative 4. 10 minus 12 is negative 2. 12 minus 12 is 0. 14 minus 12 is 2. 16 minus 12 is 4. And 18 minus 12 is 6. If I added those up to find their mean as they are, I would get a 0. So I'm going to square each one. 36, 16, 4, 0, 4, 16, 36. Then find their sum. Which is 112. And now I'm going to undo that square part to take the square root of the average, but instead of dividing by n, I'm going to divide by n minus 1. 1, 2, 3, 4, 5, 6, 7. So I'm going to divide by 6. Let's see what that is. 4.32. Okay, let's do it again. Let's find the mean by adding these up. 6 plus 7 plus 8 plus 12 plus 16 plus 17 plus 18 divided by 7. And I get a mean of 12. Again. Okay, and the range is 18 minus 6, again, or 12. Let's find the standard deviation. This time my data points are 6, 7, 8, 12, 16, 17, 18. So the deviation of each point from the mean, 6 minus 12, negative 6, 7 minus 12, negative 5, 8 minus 12, negative 4, 12 minus 12, 16 minus 12, 17 minus 12, 18 minus 12. I've got to square them so that it doesn't add to give me 0. And now I'm going to find their sum. And to find the standard deviation, I'm going to square root 154 divided by n minus 1. Again, my n is 7. So 7 minus 1 is 6. .07, rounding to the nearest hundredth. Okay, and one more time. Let's find our mean. So in this time I have 3 6s plus a 12 plus 3 18s. So that is 7 items again. Which gives me, hit the right key on the calculator, I got to redo that, I hit a wrong key, which gives me 84 over 7 again, so 12. Range, once more, 18 minus 6, which is 12. And then the standard deviation requires a table where I can list all of the data points individually. Find their deviation from the mean, which is 12. So 6 minus 12, 6 minus 12, 6 minus 12, 12 minus 12, 18 minus 6, 18 minus 6, 18 minus 12 is 6, 18 minus 12, 18 minus 12. To avoid that 0, we're going to square each one. Sum them up. This time that's 6 36s that I need to add together. I didn't put my sum under here. Okay, so my standard deviation is, I still need to divide by 6. So 6. Okay, now it has asked me to describe one way in which the samples are alike. Well, they all have the same mean. They all have the same mean, or they all have the same range. And one way in which the samples are different. They have different standard deviations. Or, notice how the one with the smallest standard deviation, they are kind of spread out more evenly from the mean of 12, right? This one's a little bit larger, so here's my 12 still in the middle, and I've got, you know, this one is 4 points away, 4 points away, and then 5 away and 5 away. So they're spread out a little more. I don't have any as close as like the 10 and the 14. But over here with the larger standard deviation, they're all, right, 6 points away from the mean, every last one of them. So these are spread out farther from the mean than these, and these are spread out even farther from the mean than these. That's what the standard deviation tells us. The smaller the number, the smaller the spread of the data atoms. The larger the number, the larger the spread of the data atoms. Okay, I'll see you in the next round.